Hello and welcome to this review of the MetroHit Energy made by German manufacturer Gossen Metrawatt. The Energy, that is not only a multimeter but also a power meter from the microwatt range with a resolution of 10 nanowatts up to the kilowatt range, and furthermore it offers a number of special measurement functions. In addition to usual measurements, we will also see some of these special applications in this video. The focus is again on practical application. Moreover, the Energy can also record up to 300,000 readings with date and timestamp and can be used as data logger as well. So a quick look at the corresponding computer software must not be missing. This video is intended to give an overview of numerous functions based on concrete measurements, and therefore it is quite comprehensive. At first glance, you notice the automatic socket blocking mechanism originally developed by Metrawatt. This blocking mechanism is linked to the rotary switch. After the test leads had been plugged in, the blocking mechanism prevents the user from turning the rotary switch to inappropriate measuring functions. For example, from volt to ampere or from power to capacity measurement. So the automatic socket blocking mechanism saves one or the other fuse, whereby the Energy generously forgives accidental mismeasurements in all ranges, for example 230 volts in the ohm range. This is not only useful for beginners, but also for experienced professionals. The Energy has only 3 input sockets, and that is very user-friendly. The advantage is that you plug in your test leads, and then you are able to measure continuously from microamps up to 10 amps, without having to interrupt your measurement in order to plug the test leads into another socket and turn the rotary switch to another range. Of course, this also applies to voltage measurements. The Energy is not turned off and on by turning the rotary switch. Instead, it has a separate on and off key, and that has several advantages. When the meter is switched on and you briefly press the on-off key, a blue background illumination is activated. From a practical point of view, a on and off button like this offers several advantages. With a separate key, there is no effort required. You can turn the multimeter on and off with one hand and without having to hold it with the other hand. Besides, you can also interrupt a measurement and continue it later without plugging out the probes, provided there is no dangerous contact voltage applied. Whereas an on-off switch that is integrated in the rotary switch has a further disadvantage. It happens easily that you connect the probes and then turn the multimeter on, and by doing so you turn the rotary switch to inappropriate measurement ranges. For some devices, this will not be without consequences. With a separate on-off switch, safety functions can easily be realized. During measurement, the Energy can only be switched off when the voltage at the input jacks is less than 30 volts AC or less than 35 volts DC. A feature that contributes to security. The meter cannot be switched off when dangerous contact voltages are being applied, in this case the mains voltage. When the dangerous contact voltage had been disconnected, the meter switches off. The first measuring range is AC voltage, and with that we start the measurements right away. The measured mains voltage is displayed in the main display, and at the same time you can read the mains frequency of 50 Hz at the top left. Each measuring function has further features which can be accessed via the function key or via the cursor keys. Pressing the function key and the mains frequency is shown. Again function key and a 1 kHz filter is activated. We'll get to that later in detail. Press function again, and we are at the AC voltage level measurement in dB. The 0 dB reference level can be set in the menu. And we are back in the normal AC voltage range. Now I switch on to the DC voltage range and press the function key for combined voltages AC plus DC because we are still measuring the mains voltage. The top left auxiliary display shows the crest factor. The crest factor gives information about the waveform characteristics of the signal. A clean sine wave has a crest factor of 1.4, or exactly the root of 2. The crest factor is calculated by dividing the voltage peak value by the RMS value. Not every meter can handle higher crest factors and non-sinusoidal waveforms, which are common, for example, at phase-fired controllers. Conventional, cheap multimeters are usually designed for purely sinusoidal waveforms. However, with phase-fired control, you do not necessarily have a fully shaped sine wave, but you may have only sections of a sine, depending on the position of the potentiometer of the PFC. In this case, the brightness of a light bulb is controlled by a phase-fired controller. The cheap red multimeter on the left has its difficulties with higher crest factors, and displays voltage values that are not true, whereas the energy easily measures the voltage and shows accurate readings. The next two subfunctions are about event recording, DC and AC. You can set up a low trigger and a high trigger threshold in the menu, and whenever a measured value exceeds or falls short of the threshold, a high volt or a low volt event is recorded. Pressing the function key again, and we are back in the normal DC voltage range and can, for example, measure a battery. At the moment, the automatic range selection is active, so the meter sets the decimal point automatically at the appropriate position. While doing so, it is absolutely normal that the meter displays overload for a short time. If this bothers you, simply switch to the manual range selection to select the measuring range yourself. This is done via the cursor keys. Press function and we see the crest factor again. With pure DC voltage, the crest factor is 1. The energy can directly display combined voltages. That means voltages with a DC component and an AC component. In this measurement, the AC component is 4.1 volts, and the DC part is 7.4 volts. The result is 8.46 volts AC-DC. With stable AC and DC values, you may calculate the combined voltage, but with fluctuating values, it is very comfortable just to look at the multimeter and just read the combined voltage value on the display. Combined currents, AC plus DC, can also be measured and read directly. Let's briefly calculate this. 259 milliamps DC with 143 milliamps AC component equals a combined current of 295 milliamps AC plus DC. This function is particularly useful, for example, for measurements of pulsed charging currents. Relevant is not only the power source, that might be a power bank as well. What matters too is the charging circuitry in the device, such as a mobile phone, for instance. Here, for example, a battery is charged. at the moment with pure direct current, and all measuring instruments agree and show the same readings. Now I switch to pulse charge, which is often helpful for charging or regenerating batteries, and we'll see the difference. The energy reading shows the combined current AC plus DC. Only measuring DC, however, does not provide a reasonable result. As you can see, voltages and currents with AC and DC components easily lead to erroneous measurements. Therefore, it is always a good idea to check whether there may be combined currents. To do so, you measure DC and additionally AC. And if you get a measurement result both times, then it is usually a current composed of AC and DC. This is also true for voltages with AC and DC components. The energy is equipped with a switchable 1 kHz low-pass filter. When the filter is activated, it is indicated by the display. At the moment, we measure a 50 Hz sine wave with 1 volt RMS. The signal is fed into the multimeter and simultaneously into the oscilloscope. On the scope screen, we can observe the signal. There you can see the frequency of the signal, and you can also see that the voltage of the signal does not change when we increase frequency. At a frequency of 1 kHz, the filter should ideally reach the -3 dB point and the voltage should drop to 70.7%. That means at 1 kHz we should see a reading of about 700 millivolts on the multimeter. Now I'm increasing the frequency. At about 700 Hz, the low-pass filter starts to work. At 1 kHz, the displayed voltage is around 700 millivolts, which corresponds to -3 dB. So the 1 kHz low-pass filter works exactly as it should. When I set the frequency to 50 Hz again, the low-pass filter does no longer attenuate the signal, but let it pass, and the meter shows 1 volt. With the filter being deactivated, 1 volt is measured continuously, regardless of frequency. The low-pass filter is helpful for all measurements on devices that tend to generate harmonics, such as variable frequency drives, phase-fired controllers, and so on. This variable frequency drive is connected to a fan. The frequency is set to 40 Hz, and both multimeters measure the corresponding voltage. The meter on the right, made by Metex, had once been expensive, and it is still good, but it cannot cope with a variable frequency drive, and it is not the only one. However, this is not a challenge at all for the Metrowatt Energy with its 1 kHz low-pass filter being activated. The energy accurately measures voltage and frequency. Even with the filter being deactivated, there is just a slight deviation in voltage, and the frequency measurement is precise. Since variable frequency drives generate many harmonics, conventional multimeters usually have difficulties with frequency measurement. The variable frequency drive here is set to 41 Hz. That is exactly what the energy shows. whereas the reading of the multimeter in the right shows 7.7 kHz. Sometimes the measuring points we would like to contact are in an unfavorable place. For those cases, the energy offers the auto-hold function that is implemented in a number of Metrawatt meters, including the energy. With this feature, we do not have to turn our eyes away from the measuring points in order to read the multimeter. As soon as the measured value is stable, the meter outputs a beep and freezes the reading with a timestamp. This allows the user to conveniently read the value on the display even when the test leads had been removed. The first auto-hold measurement is performed in auto-ranging mode. Once a measured value had been recorded, the multimeter switches to manual range selection. That is why it is necessary to activate auto-hold again for further measurements. Auto-hold in the millivolt range generally requires the millivolt range to be selected manually. In the switching position PQ, short for power quality, the energy monitors the mains voltage and records disturbances. The reading shows the current measurement value, and simultaneously overvoltages and undervoltages, peaks and transients are detected and recorded. The parameters can be set in the menu, where you can define the mains frequency as well as the limits for over and under voltages, peaks and transients. First, I start data recording. And now mains disturbances are simulated for testing purposes. The number of recorded events appears at the left-hand auxiliary display. Now I stop data recording. The recorded events can be browsed directly at the push of the cursor buttons. We see time and date when the disturbance occurred and the corresponding voltage value. Using the infrared adapter and the software, you can easily evaluate the recorded data on the PC, for example in form of a YT diagram. The value at the mouse pointer position is shown below. This is great especially for long-term monitoring because disturbances, which are additionally highlighted in color, can be detected easily. You can also view the data in form of a list. It is convenient that you can change the time axis. At the moment, the relative time is displayed. That means the starting point of the data recording is 0, and the values after that indicate how much time has passed since the start. But you can also switch to absolute time, and then you can see the time at which the disturbance occurred, for example at 5:06 p.m. But more about the software later. Pressing the function key leads to harmonic analysis. Here we see 3 harmonics. The signal that is fed into the meter is displayed at the same time on the oscilloscope. The reading shows the THD value, the total harmonic distortion. That is the ratio of the total true RMS value of all harmonics to the true RMS value of the fundamental frequency. The fundamental frequency can be selected in the menu. The individual harmonics with distortion component are displayed too. Here we see 3 harmonics. Up to 15 harmonics can be analyzed this way. The input sensitivity of the counter is very high. You can already read the 50 Hz when the test leads are touched. At the moment, we measure a rectangular signal with 50 Hz. Simultaneously, you can see the signal on the oscilloscope. The duty cycle is the ratio of the pulse duration to the total period of the signal, and it gives information about the on and off times of a rectangular signal. For a resistance measurement, I use this precision resistor with 0.1% tolerance and 2 taps. One with 3.3 kiloohms and the other one with 11.11 kiloohms. When measuring low resistances, the cable resistance of the test leads and contact resistance can be eliminated by setting a 0 point. To do so, in resistance measurement range, you connect the ends of the test probes and the multimeter shows their resistance. Then you press the 0 key and the reading shows 0. From now on, the energy automatically subtracts the resistance of the measuring cables from the measurement result. This way, you can directly read the pure resistance of the component you are measuring. The 0 point setting is cleared by connecting the probes and pressing the 0 key once more, or when the multimeter is switched off. With the 0 key, you can also activate the relative value measurement function, which is very helpful for comparative measurements. 0 and relative can also be combined. The relative value measurement function is available for different measuring ranges. As an example, we measure a 100 ohms resistor. I press the relative key, and the current measured value is set as reference value. If you now measure another resistor, the reading shows the difference to the stored reference value. The value of this resistor is about 4 ohms less than the stored reference value. And this one deviates by 2.4 ohms. The relative function is helpful when you are looking for components with as identical values as possible. With automatic range selection, the relative value measurement is available up to 25,000 digits, which is about half of the full measuring range of 60,000 digits. In case of the energy, the ranges are divided into steps of 6. In the 6-volt range, the reference value should not exceed a maximum of about 3 volts. In the 60-volt range, it should not exceed about 30 volts, and so on. With higher reference values, such as 5 ohms or 5 volts, it is necessary to manually select the measuring range and set it one range higher. The advantage of the 5-digit display turns out again. You can select a range higher and still have enough decimal places. The energy measures resistors with less than 1 ohm astoundingly well, although it does not replace a milliohm meter. In addition, it is equipped with an RSL low resistance measurement function. First, we measure this 500 milliohms resistor in the normal resistance range. With probes connected, I set the 0 point so that the resistance of the measuring cables will not be taken into account. Most multimeters have difficulties with low resistance values, but the energy handles that extremely well. Same again with the RSL measurement, which works with a higher constant current of 3 milliamps. For RSL measurement, a threshold up to 60 ohms can be set in the menu. If this limit is exceeded, an acoustic warning sounds. Continuity test does exactly the opposite. There, the sound is output when the threshold is fallen short. The fact that both functions are available is ideal for resistance and cable measurements. The energy is also able to measure electrical conductance in nanosiemens. The continuity test responds fast and without delay at closing and opening. The limit value for audible response can user-defined be preset in the menu. By pressing the function key, we get to the diode test. The instrument displays the forward voltage. Zener diodes can be tested up to a maximum of 6 volts. It is a pity that no temperature sensor is included in delivery, but it is very convenient that you can use both the K-type as well as PT100 and PT1000 temperature sensors. The next point is capacity range. As we do not want the capacitance of the test leads to affect our measurement result, we first press the key for zero balancing. In capacity range, the measuring lines should be open and not be connected to each other when pressing the zero key. Before measurement is performed, always make sure that the device under test is voltage-free and discharged. The capacitor here has 1.5 microfarad. By pressing the function key in capacity range, we get to the cable length measurement. This cable is 7 meters long. The measurement result agrees with this. Of course, the cable should be powerless and have the same characteristics throughout, so make sure that the cable is not made out of varying cross-sections or materials. The cable parameters should be identical. For accurate results, the capacity of the cable per kilometer should be known. By default, a scaling factor of 100 nanofarad per kilometer is preset. The scaling factor can user-defined be entered in the menu. The reading for this rolled-up cable reel is correct too. A bar graph would be nice, but it's not a must, because the energy is primarily a power meter, and it is very fast, and has a peak hold function that automatically records short-term peak values in the DC range. This is very useful for measuring inrush currents, for example. Inrush current is the maximum current drawn by a device at the time it is turned on. The inrush current of this small DC motor is 293 milliamps, and that is significantly higher than the approximately 70 milliamps during normal operation. The inrush current of this larger DC motor is 4.5 amps. In operation, it draws about 1.9 amps. Next, we look at the inrush current of a light bulb. The measured peak value can be read even when the measuring object is no longer connected. The inrush current of light bulbs depends, of course, on the temperature of the filament. The warmer the filament, the lower the inrush current. In addition to peak hold, there is a minimum-maximum function. We continue with power measurement. It is a big advantage that the energy is a portable handheld power meter that offers the opportunity of mobile use. It is outstanding that the power measurement starts in the microwatt range. The energy measures from microwatt to kilowatt range without the need to switch the range and plug the test leads into another socket. That is excellent and essential, especially for laboratory use. A short insertion in the microwatt range. The decimal places are in nanowatt. I do not know any portable power meter with this accuracy and resolution. Here is the resistive load. Now I increase the voltage so that you can see the range switching. The two auxiliary displays show voltage and current. Here is the range switching from microwatt to milliwatt. Now I decrease the voltage and the power decreases too. Of course, this works perfectly well with AC too. The energy is absolutely fascinating. Here we see two identical original power supplies. Power measurement will reveal the difference. At idle, the power consumption of this power supply is 470 milliwatts. Now we compare this with the other identical power supply. And the power consumption is only 82 milliwatt at idle. Another power supply from a different manufacturer is about 86 milliwatts at idle. When charging, it is about 3.9 watt. When I lock the phone so that the display turns off, the power consumption drops to 2.8 watts. With the display being on, it is about 800 milliwatt higher. When you press the function key, you can see the total consumption so far, like an electricity meter. Top right, the runtime. Once cursor to the right, and you see the apparent power in volt ampere. In AC circuits, inductors and capacitors cause a phase shift between voltage and current. That is why we do not only have real power, but in addition, apparent power and reactive power. Apparent power is measured in volt amps and symbolized by the capital letter S. It is the product of voltage E and current I. By dividing real power by apparent power, you get the power factor, in the meter display abbreviated with PF. The power factor is also known as cosine phi or lambda. In this case, 3.58 watt real power divided by 7.46 volt amps apparent power is a power factor of 0.48. The instrument shows the power factor with a sign. A negative power factor, such as minus 0.48, means that the phase shift is capacitive. A positive power factor means the phase shift is inductive. The value 1 means voltage and current are in phase. Knowing the power factor, you can calculate the phase angle between voltage and current. With a power factor of minus 0.48, the phase angle is 118.7 degrees. With a power factor of 0.48, it is 61.3 degrees. At first glance, these are different results, but in principle it is the same, just from another point of view. By multiplying apparent power by power factor, you get real power. For calculation, you can ignore the sign of the power factor. 7.46 volt amps multiplied by the power factor of 0.48 is 3.58 watt real power, which corresponds to our previous measurement result. Reactive power, symbolized by the capital letter Q, is measured in volt-ampere reactive. Reactive power equals the product of apparent power and the sine of the phase angle. We have already calculated the phase angle using the power factor. That was 118.7 degrees, respectively 61.3 degrees. 7.46 volt-amps multiplied by the sine of 118.7 degrees is a reactive power of 6.5 volt-amps reactive. With a phase angle of 61.3 degrees, we get the same result. Important is that the sign of the power factor gives information on whether the phase shift is capacitive or inductive, whether current is leading voltage, or the other way round, current is lagging voltage. For power calculations, the sign does not matter, as power cannot be negative. Reactive power can not only be calculated with the phase angle, but also with apparent power and real power. Both auxiliary displays show the measured voltage and current. Cursor to the right, and we are back at real power measurement. From power measurement, we can switch over to the current range, where we can see the crest factor, which is about 4 for this switching power supply. Next, we take a look at a power measurement of a variable frequency drive. For testing purposes, it drives a fan. The fan is set to the highest level, but the frequency is only about 20 Hz, and so the fan turns slowly. Real power is about 4.7 watt. Now I increase the frequency up to 50 Hz. Rotational speed and power consumption increase too. But that works only up to a certain limit. If that limit exceeded, the motor can no longer handle the frequency. When I increase the frequency up to approximately 70 Hz, then the fan does not get faster, as one might expect, but slower, and the power consumption increases. At approximately 90 Hz, the power consumption is higher, and the rotational speed is lower. This is only for demonstration purposes. In the longer term, the motor would not tolerate it. At 50 Hz, the real power decreases to approximately 28 watts, and rotational speed of the fan increases up to the normal level. At 60 Hz, the speed is slightly higher, which would also be fine in this case. Which frequencies are suitable for a motor and which are not depends on the motor type. The auxiliary displays show voltage and current. In this case, voltage is 190 volts because this is a three-phase variable frequency drive, but it is operated with 230 volts mains voltage only. For the measurement itself, this has no significance because this fan can only be controlled by frequency, but not by voltage. Apparent power and reactive power can also be measured. In DC circuits, power measurement is straightforward. To get real power, you just multiply voltage E by current I. Nevertheless, it is very pleasant and convenient when the multimeter directly displays the power. By pressing the function key, you can see the total energy consumption and the time that has passed by so far. In DC circuits, the power factor, or cosine phi, is 1, so we can ignore it for calculations. Apparent power is identical with real power. Consequently, there is no reactive power. For devices with Schuko or Europlugs, an intermediate power measuring adapter is highly recommended. You can purchase it or just build it yourself, like the one in the video. But devices do not always have power plugs, and for those cases, I quickly built myself a small measuring adapter. It is wired like this. On the left side, you can see the input plugs. There, you connect the power source either via banana jacks or via the clamped connectors if there are only 2 wires. The load you want to measure is connected to the plugs on the right side, again via banana jacks or via clamp connectors. The plugs in the middle, with a green border around them, are connected to the multimeter. This makes wiring much easier. With some additional adapters, for example from USB to banana jacks or others, you are prepared for every kind of measurement. Practical usage looks like this. The power supply is connected to the measuring adapter via banana sockets. The bulb is connected via the clamp terminals, and the energy shows the power. In DC circuits, the real power in watt is identical with the apparent power in volt amps, and there is no reactive power. By pressing the function key, you will again see the energy consumption and the runtime. If the measured value does not change for a preset period of time and none of the keys or the rotary switch have been activated, the energy automatically shuts off. The period of time until shutdown can be user-defined preset in the menu. Here it's set to 50 minutes. It can be adjusted by the cursor keys. The multimeter is continuously on without any further action required when switched to PQ power quality and power and energy measurement. Continuous operation is manually activated by pressing the function key while switching the multimeter on. The letters ON right next to the battery symbol in the left corner of the display indicate that the meter is continuously on. The next time you switch the multimeter on, but without pressing the function key, the automatic power off is activated as usual. On the rear side, there is a separate fuse compartment and the battery compartment for 2 AA minion batteries. Since the energy is also a data logger, time and date are maintained by the batteries. If you completely disconnected the device from the batteries when switching off, you would have to set the date and time each time you turn the meter on. In switched off state, the current consumption is about 72 microamps. That is the supply for the internal clock. Switched off, 2000 milliamps batteries would last about 3 years. Regarding such periods, there is a greater risk of batteries leaking. I check and replace them at least every 2 years. If you really do not use the device for a long period of time, just store it without batteries. In order to facilitate the measurement of current consumption with batteries inserted, I built some time ago a measuring aid from a part of a shielding. You could also use a thin double-sided board or similar things. Both conductive silver surfaces have pins for the test leads on each side. And of course, they are isolated from each other. The 100 nanofarad capacitor is meant to avoid interference. On the top of the meter, there is the jack for the power adapter. This connection is for the optional infrared interface adapter in order to connect the meter with the computer. In the middle, the optical transmission takes place. The slots left and right are recesses for the brackets. In this way, the PC and the measuring instrument are galvanically isolated. The adapter is connected to the computer via USB. If you use the energy more often, you might want to supply it with a power adapter. It would be nice to see whether the device is powered by batteries or by the power adapter, because the power supply may fail for some reason. For example, the battery symbol could disappear whenever the meter is powered by the power adapter and not by batteries. Usual magnetic fields in the measurement environment or in the control cabinet do not affect the multimeter in any way. One or the other would like to place a strong magnet on the energy. The meaningfulness of such supposed tests is more than questionable. First, such measuring environments are completely unrealistic, and second, relays usually switch with a magnetic field. Due to the lack of informative value, this was waived. This video does not insert datasheets either. Anyone can view them on the internet anyway. Instead, this video gives preference to practical measurements and applications. Far more measurements and tests were performed than can be seen in the video. The energy throughout meets the specifications. That is what data logging with Metrawatt looked like in the 1960s. This electromechanical masterpiece, a Servo-Gore chart recorder, is now about 50 years old, maybe older, and it works perfectly well. The special thing about it is that you can not only use continuous paper, but also normal A4 paper. I do not have an original pen for it. That is why a usual gel pen is used in a self-made plexiglass holder. Unfortunately, the pen is a bit too long and therefore swings slightly. But that is just a side note. Of course, Metrawatt can record data even better today. The energy has its own internal memory to record data. Data recording can be started and stopped on the meter. The parameters, such as the sampling rate, can be set in the meter menu. Additionally, they can be set via the MetroWin software. Furthermore, the software is capable of controlling the multimeter remotely. It should be emphasized that the MetroWin 10 software runs from Windows 98 up to Windows 10 and requires a screen resolution of only 800 × 600 pixels. That is a great advantage for all those who use older computers or notebooks for their electronics and measuring applications. Another excellent item is that the software does not require an internet connection. The help function is available offline in form of a PDF document. Currently, the energy is connected to the computer via the infrared adapter. And now we are reading the meter's memory. Get Memory Info checks whether data are stored in the multimeter. If so, you can read and save them as file. And of course, we will look at the data right away. First, as list. And then in YT view, where you will recognize the stairs from before. The axis can be adjusted manually or zoomed with a mouse in order to take a closer look at interesting sections. The data at the mouse pointer is shown below in digital form. Once data had been saved and archived, you can reload it later at any time. During power measurement, several values are recorded simultaneously, such as real power, apparent power, reactive power, the power factor, and so on. In YT view, the values are shown in different colors. Below, they are displayed in digital form. Here, the outlet was switched on. At this point, the mobile phone charger was plugged in and is consuming about 80 to 90 milliwatts at idle. From here on, the mobile phone is charged. Real power, displayed in blue, increases to approximately 4.5 watts. At that point, the mobile phone display was turned off. The power consumption is decreasing slowly. Of course, you can also analyze the data in form of a list. Altogether, the software offers various capabilities to evaluate data. In addition, you can set all the multimeter preferences with this software. You can personalize your meter and you can remotely control it without any need to turn the rotary switch. Just open the Setup Device dialog, click on Search, and then read the multimeter's settings. Next, you can change the settings of the meter using your computer and send your custom preferences to the multimeter. You can also change the measuring range right from your PC without any need to actuate the rotary switch. At the moment, power measurement is selected. Via software, I now switch to AC voltage and send the setting to the device. The meter switches to the AC voltage range without the rotary switch having been actuated. In this way, you can switch to all ranges remotely. You can also connect and control several multimeters at the same time. In addition, the software can receive live measurement data from the multimeter, display it on the computer screen, and record it at the same time. The entire test was, of course, much more comprehensive than this video shows. Of course, all measurements had been counter-checked and verified, and the energy throughout meets the specifications. Besides, the energy is solid, durable, and of high quality. My impression is very positive. I do not know of any other portable power meter from microwatt to kilowatt, and with this range of functions. Furthermore, the energy is an excellent multimeter. It convinces by precision, versatility, and a number of practical useful functions that facilitate numerous measurements. A further advantage is the capability to record data. Altogether, a very good test result. Thank you for watching.